All right. So as I said, right now, there is no way to break into any of these public key systems, and there may never be. But quantum computers, in principle, can do it because of something called Shor's algorithm. And we'll hit more detail later when we get to the quantum computing part. So there is a known algorithm, which if you had hardware that was about 1 million times better than the hardware we have today, you could crack encryption keys into RSA and any of the other public key systems. So since we're afraid that might happen in a few decades, they're trying to invent systems that cannot be broken by quantum computers. And they named them all after crystals in science fiction movies. I think Kyber is the crystal in Star Wars that powers the lightsabers or something like that. And so crystals Kyber is the cryptography system, and this is what they call a lattice cryptography system. Now, it looks to me like a learning with errors system, but I guess they call this lattice cryptography. It is very strange. Remember, RSA was very simple. All you needed was modular arithmetic and raising integers to a high power. This one is much harder to understand and sort of mind-boggling at first, but we're all going to have to get used to it. This is the way the world is going to be. So you have a vector of polynomials with small coefficients. That's the private key. Then you have a modulus and another modulus and a matrix of random polynomials and then small random error values, which is why I think this is related to the learning with errors, which is another proposed system, and then a calculated vector. So the public key is a matrix of random polynomials and a calculated vector. That's the public key. And to generate the private key, you have to, so in baby Kyber, we have a very small system of small numbers. The private key is going to be 2 polynomials. This is the first one. All the coefficients are going to be minus or plus 1 to make them small. So it's minus x cubed minus x squared plus x. And the other one is minus x cubed minus x. Those are 2 polynomials. So we generate a matrix of random polynomials and choose a modulus, and errors, which are just more polynomials with small coefficients. And then you do matrix multiplication and addition to create this thing called T. And T is going to be a calculated vector that is important. And so you have to do this kind of multiplication, which is kind of big and complicated. That whole screen is the multiplication here. 6x cubed times 9 times minus x cubed is minus 6x to the 6th, and so on. All these terms, you add them up, and you are taking the modulus x to the 4th plus 1, so you can include that. Eventually, you boil it all down, and you get this parameter. And that's the top parameter, the top polynomial, and there is a bottom polynomial. And so this is the final result, T, these 2 polynomials in an array. And so now you can take the private key. That T is part of the public key, A and T. That's what people use to encrypt messages, and you open it with this private key. And so it is pretty crazy. And you can calculate a key here. And so now it's really hard to do by hand. And so typically you're going to use Python for it. And there is not an easy library to do this yet. You have to import the Pyber script from my website, but I got it from somewhere. And so now you can define these things. This is probably an easier way to see the parameters. The modulus is a number. Then you have F is this array, x to the 4th plus 1. And here's the secret key, which is 2 polynomial coefficients. And here's that calculated value A. And here's noise, which is added. All right. So that's the game. You can calculate the public key from this mesh and practice doing that. And so to encrypt and decrypt, you have a randomizer polynomial, an error polynomial, and another error, all of these with small coefficients, which are going to go away later. They're just there to make it difficult to crack without having the private key, and then a message. So to encrypt 4 bits, we're going to encrypt the number 11 is our message in binary. It's a whole lot of work to encrypt very little message. So you encode the message, and then to make it large enough to overcome the errors, you scale it by multiplying it by a large number, which is 9 in our case. So the message has a larger signal than the noise parameters that are going to be added to it. And in the encryption process, you add these error terms. Here's another error term. Here's another error term. That's the noise. So the encrypted message has noise added, which is going to thwart decryption without the key. And all right. So when you're done, you put in, and here's the message, 1101, and here's the encrypted message. It is one array containing 2 vectors and then a solitary vector. And these are polynomials. So all these numbers here represent those 4 bits. And you can encrypt them and decrypt them after defining all these parameters. So in practice, it's not too hard to use. It just gives you a little bit of a headache to throw around these long vectors and arrays of numbers instead of just having some simple number like encryption or decryption integer like you'd have in RSA. So that's the game. You should begin the process of getting used to this. And I suppose all other encryption schemes seemed this confusing at first, but we sort of got used to them. So we're all going to be doing that pretty soon. And that's it for this one.